We have a fantastic speaker from Cornell University. Please welcome Professor Robert Shepherd.
Thank you so much for inviting me to be here. So for those of you that were at the Materials Research Society, and some of my talks here, it's going to be largely similar, so I apologize if you were there, but maybe you can take away something else that wasn't there before. So in order to make, so this talk is about material science and hyperelastic mechanics in order to enable better, generally adaptive robots. And I'll talk a little bit about why I think those are important, even though I'm not assembling them into the whole systems. And so my perspective on this is that we have two fields, some more recent than others, of smart systems, which is quite old at this point, and primarily focus on MEMS and their integration into devices. And then robotic materials, which is a newer one, which seems to be about making components for robots out of non-traditional materials. And then I've been charged by the Air Force to bring about this new field that we're calling autonomous materials, which is sort of a second or even third generation of something called autonomic materials. And it is not necessarily robotic. You could have a bandpass filter that is dependent on the angle of incidence without any motion of the device, for example, as a non-robotic system. But our group is focused primarily on mechanical motion out of these autonomous systems, which crosses significantly with robotic materials, but we believe robotic materials is a sub-discipline of autonomous materials. It's a very inventive discipline in that it's multidisciplinary, and for those of you who are interested, there are steps to invention. The first primarily is problem identification. So it's hard to build a robot without a problem to solve, although we do in many cases. And so as a material scientist coming into the field of robotics, I felt that I needed to learn what problem we were solving and learn the field of robotics, which I have not done. I've tried. It's very hard. And so then with it, from what I do know, try to question some of the assumptions that are presently there, and then apply maybe the material science discipline that I do know to some extent to solve it. And then one of the methods of invention is substance field analysis. Apply it there, identify bottlenecks, and see how we can solve them. So for myself, I'm very passionate about solving a disparity in nutritional needs. And in one way is through agriculture. And then a lot of people are like, well, people aren't starving anymore. They actually are. You just don't see it on the news as much now. And there is an excess of food at the endpoint, but the logistical distribution of food is a severe problem that needs to be solved. And I think one way to solve it is technologically with robots, but wealthy economies can afford robots specific for a task. But developing economies can't really afford very highly specified robots to solve these particular problems. What could happen is for generally adaptive robots to be produced, something like Spot, but that then other economies could adapt for their particular needs. So one solution we're hoping is to enable generally adaptive robots to solve the nutritional crisis that our world faces, but by adding components and abilities from the material science perspective. And to do that, we're creating robots that we think will have application in agronomy, whether for studying the science of plant transformations or improving yield or reducing or increasing diversity of crops. So how we are going about this is applying substance field analysis to robotic systems. And if you look at Spot, which is a really, as you all know, an important general purpose robot that people are buying and adapting to specific needs. And in most of, I think probably all quadrupedal robots at this time have some kind of rubber pad at the bottom of the feet, which is really critical to enabling gaits in these quadrupedal robots. And so if you were to apply substance field analysis to Spot, you would have a really complicated functional decomposition map, and then you'd zoom in on one area, which would be the foot contact with the ground. You'd have two substances, the foot and the ground, and the field being a mechanical field between them. One of the thing that this rubber does is apply spatial filtering to the ground. It allows a different response autonomically or automatically based off of the texture of the ground. If the ground is very rough, on the order of the thickness of the pad, it can deform around that and allow stability. If the ground is very flat, it can absorb more energy, store it, and release it in a more elastically efficient way. And it does this all without the typical types of feedback control that is used, that we might apply to a more traditional robotic system. But what we don't have, anyway, I'll get to that. So anyway, coming from my perspective, without having a formal training in the field of robotics, the problem to solve, the high-level problem to solve, is addressing additional nutritional needs logistically through generally adaptive robots. The more specific problem to solve is an engineering contradiction between endurance, which we get in autonomous vehicles by spending a lot of money to make roads, and agility, which we can get through legged robots, but they can't do this for very long. They have low endurance. And so how do we solve that contradiction? If you use TRIZ, which is a parametric approach to invention, you can input this engineering contradiction and output historical solutions to this problem. One of the solutions is make movable parts fixed and fixed parts movable. So that example is represented very well in Handle, where they put wheels on as the feet of the robot. So now it's enduring and adaptive. It's not as adaptive or agile as if it had real feet, but it's a good compromise. The field of soft robotics, if you also enter in that contradiction, has another solution, which is make rigid parts flexible. And that's sort of the whole field of soft robotics, and that was codified by Genrich Altschuler, who developed TRIZ a long time ago. And this has been arrived at intentionally, I believe, in the legged robotics field by putting these pads on. So now compliance is built into feet, but that's a completely passive response to the ground. Currently is no sensing in the feet, and the degrees of freedom at the feet are zero. So there's agility is still limited, and as a result, the efficiency and endurance of these legged systems are limited as well. And so we're hoping to add material science capabilities to these systems to improve both. I gave a talk about this somewhere, and this person named Jonathan Nolan was in the audience. And I believe I've messed this up, but let me try and play a video. Yeah. Okay, so this, if you've seen it, is the introduction to Westworld. In order to make the generally adaptive robots in Westworld, you have to embrace complex manufacturing techniques. The multifunctional, overlapping systems required to have a lot of energy, a lot of adaptability into robots just requires it the same way organisms require organ systems, which are multifunctional and interconnected. How do you do that when we are building our robots right now from the top down and bolting things together, and you have to wire things? It's incredibly complicated. It's impossible to get a complex system this way. In this movie, and I talked with him for hours about this in this series, he was fully inspired by additive manufacturing, and as you know, I'm inspired by him in this work. In this universe, he uses multi-material 3D printing of rubbers and ceramics, and other things, metals and mixes of each, to achieve complex function, high resolution printing, nanoscale to even centimeter scale, so a high range of that. And then dynamic, where the things you print at the end are moving. I will never call it 4D printing because it's silly. So anyway, and then printing these things, but So we've made a choice in my group to focus on a particular type of printing, which can do some of these things, but not all of them, and then try to solve some problems there in order to enable synthetic organisms as generally adaptive robots. The first goal is robot flesh, which is sort of the easiest thing to understand from soft robotics. The idea being that compliance is very important to get great affordance with low precision instruments. Our motors, our electromagnetic motors, are more precise than our musculature. It's just we can overgrasp and still pick things up based off of at least some things like compliance and the deformation of our tissue. But the thing that biology does better than human technology by far is high surface area to volume ratio structures and very complicated structures that can do that because it has nanoscale self-assembly. And that, while many people better than me are working on nanoscale self-assembly, it's going to be a long time before that results in robots that we find useful. Additive manufacturing is a good way to get at that now, and that sort of combines Jonathan Nolan's idea and what we're doing here. And here's an example of why high surface area to volume is important. So in order to power our 600 muscles, we need to consume a lot of oxygen. And we do that by having a 1,000,000 centimeter squared area of lungs that diffuses oxygen over a micron in thickness that can deliver 1 billion trillion oxygen molecules per second to our muscles that allows us to move. It's 2.5 times the oxygen we actually need. If we built humans or animals like we do our machines, we would have pipes that transport some mass over much smaller areas and then that oxygen would have to diffuse over much longer distances, which would allow for only simple life. So the reason, so this is one reason that high surface area volume structures are important and are important in one of the research thrusts we have. In order to create these high surface area volume structures, there are lots of 3D printing techniques we could choose. We go for a stereolithography technique, which is actually a digital light projection technique, which forms a sheet at a time. As you play a movie and pull your parts out, you can produce things at an order of magnitude or maybe more higher throughput than you can with other printing systems. The downside is it's pretty hard to do more than one material at a time. And that's a constraint we've embraced. And it actually works well in a high surface area volume structure because you leave a lot of volume on the interior that you can fill with other materials. Also, DLP is a great printing method because you can print rubbers really well. Very, very good engineering quality rubbers, which biology uses to a great extent, much more than metals because it doesn't have fire to make metals. And then generally, I bring this up because I point out that when animals interact with nature, they bend and they're dynamic in their interactions. Whereas when we build our artifacts, they're designed primarily to stay the same shape until they break. So if nature bends, doesn't break, our artifacts usually break and don't move, at least where they're, unless they're hinge based. So when we started working in this space and using DLP printing, there wasn't a very resilient material available to print with. Silicones weren't printable at the time. And so we chose to use a mercaptosiloxane, or these thiol groups, and bond them using a click chemistry with a divinyl siloxane. And by tuning how long these polymer chains are and how many of these bonding sites there are, we could tune the rheology, or we could tune the mechanical properties of the printed structure very well. The viscosity we could keep really low, which is important so that these materials flow in these printers. And then the result is that we could tune our stress strain curves really well. And that after we got the mechanical properties we needed, whether it's a fairly stiff structure in the end, a very soft structure in the end, it was very resilient. So we could perform these high strain cyclical loads and then have the mechanical properties be the same every time. This is very important because maybe you've used printers in the past that say they're going to be soft, but then they break after a couple of cycles. So this is a pretty important result. And then okay, I'm trying to move forward. Okay, but then, just a couple of years later, these printers became commercially available with really great material properties. This is a carbon DLP printer that we use, and it's just showing a very complicated high surface area to volume structure made out of polyurethane. You can cyclically load this for millions of cycles and it's okay. They actually, Adidas uses it in their shoes, some of their shoes. And so this intricate programmatic foam lattice structure, we can do things like put paths in there to feed other functional materials. And we started to do things like printing using topology optimization and printing of things like morphing wings, which can extend and contract. We skin this later so it's aerodynamically efficient and twist and bend. And we start putting sensors in here so they can feel its shape. We did things like make this prosthetic or robot hand that can that has the motor, the 6 motors, the controller, and the power on just in the palm of the hand, and still weighs only 370 grams, as well as flexible PCBs in the fingers with time of flight sensors that can see things approaching it and then grab it. The real innovation here is the passive transmission systems in there that allow it to close quickly, and then after it grabs on something is to reduce the circumference of these spools so that it can apply high torque. And this is because it's a very complicated, interconnected, multifunctional system on the inside, which I don't have time to describe fully. We added more capabilities to our materials that we can print. These are put sulfonated silicon nanoparticles on the inside of these hydrogels that we can then print. And after printing, it's electrically functional. So we can apply an AC field to this bear, which we stab with an LED. And then the diode allows current to pass and emit light. But so you can print electrical conduits now in 3 dimensions this way as well, while getting transparency and high resilience and extensibility. I think I'm gonna just skip past this because I don't have much time. Whenever you see a fluidically powered robot, like a hydraulically powered soft actuator, you have to both change the shape and stiffness at the same time. This is different than what happens in biological muscle, where you can change the shape and stiffness somewhat independently of each other. And so what we did to address this problem is, instead of using a liquid or a gas to pressurize and actuate these balloons, we used granular material like other people had done before. You can use granular material to cause stiffening, variable stiffness of a structure. But because previously people had been using granules that were hard to transport, like coffee grounds, you couldn't move these granules from one actuator to another. By using hollow glass spheres, which have a density of something like 0.02 grams per cc, and they're also very smooth and spherical and roll past each other, you can move this force transmitting medium from one actuator to another. And then once it's there, you can jam it. So you can actuate with the low density more like a pneumatic, but have the incompressibility more like a hydraulic. Okay, so that is how we, as far as I know, I have another 5 minutes. Yeah. Okay, so that is how we add agility, is with high surface area volume structures, high degrees of freedom, while having some weight efficiency. There's a lot more to it than that. But with all these capabilities and the future capabilities, I believe we will have towards something like hundreds of degrees of freedom in using these methods. We need to be able to, I think, feel the environment and respond to it instead of just seeing the environment. So for that, we use, we believe, just like animals, we need to have touch sensors, hyper redundant touch sensors in our skin. To get there, we've created these stretchable light guides because they're very easy to make and very resilient and low hysteresis. We can stretch these fibers thousands of times with no change in signal, very hardly detectable change in signal, with high signal to noise ratio. And again, they're pretty easy to make. So we're shining light from one side of the fiber to the other, detecting with photodiode or phototransistor, depending on the application. And that light modulation gives us information about how it's interacting with the environment. So we use high index of refraction polyurethane is the core, and a low index of refraction silicone is the cladding to trap light. As you stretch the fiber, the rays actually go through a longer path, which absorbs them more. But also, if you deform them and the curvature exceeds the critical angle that the rays are in, you lose light in both ways. So depending on the type of deformation you're encountering, you'll get a signal modulation based on both of those options. By adding wavelength as well as intensity, you can decouple those and you can figure out what type of deformation is occurring as well as the magnitude of the deformation. Or you can have multiple fibers interact with each other. And if you don't have the cladding, when they touch, you couple light from one into the other. If you have a 3D network of these multiple fibers, you can start, and you add a load, you can touch multiple fibers together by knowing where they are located, determine where that stress is being applied, and the intensity variation tells you how much stress is being applied. You can see that here. There's 12 of these fibers, uncladded fibers, that are threaded into this printed flesh. And as they're being pushed into each other, we're able to reconstruct from the raw data the type of deformation. Since we printed the center of this cylinder to be more compliant than the extremities, that's why it's deforming in the middle first. Because these fibers are so simple, they're damage tolerant. So we can punch holes in it and still transmit light through it in bending or in stretching. But what happens is, of course, there's a less light propagated as it's damaged. So we have to be able to account for this damage in the controller to know what's going on. We're still working on that. But if we cut it, we actually get a very significant signal that we can assume is a cut that we then update our controller with. We also made this out of a self-healing polyurethane urea chemistry, which after you cut, if you touch it together, hydrogen bonding allows rapid healing. And then a disulfide exchange allows strong covalent healing. So instantly it heals, but after a few minutes, it heals to almost the same mechanical properties it had before. Hidan Bai, who's really great, turned these self-healing sensors into fibers that she put onto a self-sealing robot. The yellow parts on this robot can heal or seal around punctures. They don't chemically self-heal, but the fibers do. We think we can make the whole thing out of the self-healing polyurethane urea, actually. And then she defined how the robot bends by using a flexible PCB with these LEDs and phototransistors on the board to shine light through those fibers. And this is the signal. We're not sure what that error is, but anyway, as she's actuating it, this is the signal variance. Then she'll cut it. Because of the high signal to noise ratio, we can zoom in farther and get real information. And there's a characteristic signal that happens when you apply these very sharp cuts. Allows it to heal and then update the controller based off of the new intensity that's coming through it, and then cut it again. You can keep cutting it. They used a very violent looking knife, I think, because that's what was available in Rhino or whatever. But anyway, the demo, which I'm not showing here, is that as she cuts it, it feels this cut and then actually updates its gate to move away from the cut. And then, so that's sort of the thing that happens. I don't think I have time to go into embodied energy or the autonomous materials thing, but maybe I can talk about some of the highlights later on if I have time. If you want to get involved in the autonomous materials thing that we're doing, you can take a picture of this and get involved in our Slack. We're going to have a review paper or a perspective paper that we write within the next month. Thank you.
Great talk. Thank you very much.
Thanks.
It always, well, the first half of your talk always reminds me how simple robots actually are compared to the human. I have a question regarding your shifting material robot, where you have grammar material shifting in and out. Do you use the same channel to shift that material as you use for actuation? Yes. Yeah. Sorry. We use a peristaltic pump to move the granules from one actuator to another, and then we have valving and filters that we can turn on or off. So after we transport it to an actuator, if we want to keep that shape but stiffen it, we then apply a vacuum, but have a filter in place that doesn't allow the granules to go through. Okay. That's very
All right. So much. So I'd like to start by thanking the organizers for inviting me speaking at this workshop. And thank you everybody for sticking around this late in the evening. I really appreciate you sticking here with me. Thanks also for the people that are joining remotely. It's my great pleasure to be here with you today in person, finally, for this workshop. And today I'm excited to talk about some of the recent work that we've been doing at my lab at Boston University, the Material Robotics Lab. So because we are in the session of applications, I thought I would start with the applications that we're targeting in the research that we do in my lab. And these really represent, I would say, our motivation, what wakes us up in the morning and pushes out of the bed, getting to the work in the lab. We are mostly focusing on minimally invasive surgery. So that entails endoscopic surgery. For those of you who might not be familiar with this, you might be familiar with the concept of open surgery, traditional surgery, where a patient is typically cut open and you would be able to access the surgical target area. A surgeon would be able to access the surgical target area by touching the organs. And so they would be very much involved into the surgical scenario. They would have their hands onto the organs. They would be able to see directly the organs. But then obviously there is a lot of trauma associated with that. And so long recovery times, post-operative complications, and so on and so forth. And so obviously the trend is moving towards minimally invasive surgery. Up to a point where you can insert instruments inside the body that are called endoscopes. They are flexible instruments. They are not stretchable, but flexible based on flexible optical fibers and cameras and so on. And they can basically enter through natural orifices. So think about accessing through the mouth and entering the stomach or the lungs and so on. And those represent a number of advantages from the patient's point of view, if you will. So a lot less trauma and short recovery times, but they are more difficult to operate for surgeons. And so they require longer training and they have limited motion. So the surgeon cannot obviously have a lot of dexterity inside the body. Sensor feedback is also reduced, so haptic feedback is a problem, and vision is also reduced because you only have that visual feedback from the camera at the tip of the endoscope. So those are really the applications that we have in mind when we design and build robots in the lab. We are really much in my lab, I would say, focusing on the hardware side of robotics. And so we design and manufacture the robots in the lab, and we develop manufacturing technologies in order to develop these systems. And to me, these applications, these medical surgical applications, if you will, are really case studies to start addressing questions, open questions and open challenges, fundamental challenges in robotics. So as a roboticist, I'm really interested in problems like how do we achieve safe navigation in complex and effective navigation in complex and unstructured environments. And so, for example, the colon or the lungs represent such an environment. It's really difficult to navigate within the bronchi. They branch into many different ramifications, and it's really a maze. So also questions like how do we manipulate fragile and delicate objects? So for example, think about the brain. So for example, we are targeting colorectal procedures. Colorectal cancer is one of the most common cancers within men and women across the United States and worldwide. Lung cancer is actually the deadliest cancer in the US and worldwide. It makes for more deaths than colorectal cancer, prostate cancer, and breast cancer combined. And brain cancer is actually a very difficult type of cancer to treat because you have to navigate within the brain and treat the tumor without potentially, causing harm to surrounding tissues. And so the question, how do we manipulate fragile and delicate objects in such an environment, becomes very paramount, because obviously you want, yes, to treat the tumor, but you also want to preserve neuromotor functionalities in the patient and all their, I would say, neurofunctionalities in general, so speech and cognitive capabilities as well. So all of these questions pass also to, are a nice plug to other important questions in terms of manufacturing those robots. And so if we need to achieve navigation, if we need to achieve manipulation tasks, we have to think about actuators and sensors that we want to build within these robots. And those have to be safe, obviously biocompatible. So medical surgical applications obviously come with those challenges and those restrictions. There's challenges associated, for example, with the fact that you cannot have high temperatures within the body or high voltages, high currents, and so on. So today I'm going to be focusing on 3 different classes of soft surgical robots that we are I would say investigating in the lab, and those are soft continuum robots, soft reactive skins or soft robotic skins, and soft foldable robots. And I'm gonna start with soft continuum robots, and this is a soft robotic bronchoscope that we recently developed. So for bronchoscopes, like I said, navigating inside the lungs, it represents a really important challenge in terms of navigation. And so current bronchoscopic instrumentation that you see here on the left have limitations because those bronchoscopes typically have a diameter of 5 or 6 millimeters. And so yes, they can access the bronchi, but they cannot navigate deep within the lung. And so typically 70% of lung cancer is located within the peripheral side of the lung. So really very close to the periphery of the lung. And so those bronchoscopes cannot access very close to the lung, to that position. And that obviously entails less accurate, less precise bronchoscopy biopsies. So we've developed this system that is a 2.4 millimeter in diameter soft robotic bronchoscope with 4 working channels that we manufactured out of dragon skin through molding and casting. Those microchannels that you see here are basically designed to embed a micro camera for vision-based image-guided navigation and surgical tools, for example, needles in this case. And then we have another channel here that is actually closed after the fabrication, and it's serving as a soft pneumatic chamber for providing actuation 1 degree of freedom bending. So this work was recently published on soft robotics, and here you can see the soft robot in comparison to a traditional bronchoscope. So you can appreciate how smaller it is and also the enhanced dexterity that it has. So typically a traditional bronchoscope would provide you 110-ish degrees bending angle, but in our case, we're able to bend full retroflexion, so 180, and actually more than that, up to 240 or something. And that allows you to navigate into really tiny, sharp bending angles within the lungs. So we have characterized our system in terms of mechanical performance. I won't go too much into the technical details here, but exciting results in our opinion were mostly the fact that yes, it's still the robot is able to have enhanced dexterity with respect to traditional bronchoscope system, and even with respect to robotic bronchoscope systems, which are currently available on the market, the Ion system, the Monarch system. It still presents advantages because it's smaller in diameter, and it still embeds a micro camera, which means you still have vision guided locomotion throughout the entire procedure. This is just an analysis of the 3D reachable workspace. Like I said, for now, we only have 1 bending degree of freedom, but potentially in the future you can integrate more. The bronchoscope the robot can be manipulated from the outside by using a robotic manipulator, for example, for rotating it or translating it back and forth and pushing it inside the lungs. And then we have tested the capability of the system to perform tissue puncturing, so performing biopsies. And the fact that we have 2 working channels actually is intentional because we are pushing towards having diagnosis and therapy potentially at the same time. So what traditional instrumentation allows you to do is probably a biopsy. but you only have one working channel. And so as you are performing this biopsy, sometimes you have bleeding, sometimes the camera is not working properly anymore. So we have integrated 2 working channels to potentially compensate for that. And at the same time, having 2 operative channels that the surgeon can use, for example, to inject drugs. And this is exactly what this video is showing. We are injecting dye water to simulate the injection of a chemotherapy drug. And this is basically a dream towards like maybe 5 or 10 years from now, where you would show up for a screening and they would say, well, yes, we've seen that you have lesions in the lungs and you have to go and do bronchoscopy. But what happens is typically you do bronchoscopy, but they cannot treat you right away. You have to go back. And if you test positive and they say, yes, this is cancer, you have to come back in a few months and then undergo surgery. And then potentially if surgery doesn't go well, come back again and again. And this means like months probably will pass, right? So you don't want that. You want to wake up after, a bronchoscopy procedure and talk to your doctor, and that person would tell you, well, yes, we have seen that you have cancer, but we were able to treat it. And you can come back maybe in 6 months for an additional screening. How great would that be? So we have to build soft surgical robots, in my opinion, that can enable, future capabilities like these that really can provide a groundbreaking advancement in the therapeutic capabilities that we currently have in surgical robotics. So I want to draw your attention to some of the things that we have done with the image-guided navigation with this robot. And so we have, like I said, a micro camera embedded that allows us to do, by using computer vision, that allows us to do robotic navigation within the lungs. And so we have tested that in vitro in this anatomical simulator. And by using computer vision algorithms such as adaptive threshold, contour tracking, we're able to track the bronchi within the lung and automatically have the robot steer to one of those. And so the surgeon can, in preparative planning, basically plan the path of the surgery, and then the robot can potentially navigate to the target location automatically. And so this is an example of how the robot can realign to one branch, one bronchi, and then potentially can be pushed from the outside. Another embedded feature of the computer vision algorithm that we are using is lesion location and stabilization. So once you are at the lesion of interest that you want to sample, you want to take a biopsy, it is crucial that you are accurate. And so you have to stabilize the robot in front of the lesion, but there is breathing, there is heartbeat, there is potential involuntary movements that are going on. And so it's important that the robot can track that lesion. And so once the surgeon identifies that, the robot will stabilize itself in front of that lesion if some of those accidental movements are going on. So I want to switch gears to another class of soft robots that we're currently working on, and those are soft robotic skins. And you can definitely see some overlapping with what Professor Shepard has just presented, soft optical waveguides. So the idea here is colonoscopy. Like I said, colonoscopy is another very interesting problem in terms of navigation for roboticists. Colonoscopes must be pushed from the surgeon as they are navigating to perform diagnosis, but they can basically apply too much forces onto the walls of the colon and potentially cause bleeding and even perforations, as you can see in this step here. So our idea is to develop a soft robotic skin or a soft reactive skin that can be wrapped around any type of endoscopic instrumentation. And in this case, it has soft optical sensors and soft actuators. So distributed sensors and actuators that can detect those high forces and potentially trigger the actuation of soft robotic actuators. So those would sort of like work like air balloons or airbags that then can distribute the force around, like the pressure around a larger area and help continue with the navigation. And those are soft optical sensors are basically made out of soft materials, soft elastomers that have different refractive indices, and so they can conduct light. They are biocompatible because there is no electric current, no voltage, no high temperatures, anything like that. We have obviously not only forces going on in colonoscopy, but there's also the bending and potentially tracking the shape of the colonoscope. And these are some results that we published last year on RAL. We had to put together an algorithm, a calibration algorithm to distinguish between contact forces and bending angles, obviously. And so in this case, we calibrated for forces and for bending angles. And I'm just going to quickly jump to this video where I show that I am touching the soft robotic sleeve and it's triggering the actuation. Then we are bending it, not triggering the actuation, and then touching it again. And over here, this is the force that we are applying with the instron that is actually mapped and recognized by our sensors. And so we are able to filter for bending and return to the surgeon potentially the information on the force that they are applying to the colon. This is an in vitro test on a colon simulator that we fabricated in the lab. It's just thermoplastic elastomer. And what we are doing is we're basically pushing the colonoscope inside the model, and then when the colonoscope gets stuck and potentially causes high pressure, there you go. You monitor that pressure, and those soft actuators are deploying, and so you can continue with the navigation. And so to demonstrate that concentration of forces can be picked up, we have also integrated some simple commercially available sensors here. So as we are pushing with our robot, as you can see, you are seeing just one sensor of these three picking up a force of 4.7. So a really highly concentrated force being picked up by just one sensor. And then that is obviously also being picked up by our soft optical sensors that trigger the inflation of the actuators. And what you have in the end is this distribution of force. So some recent work that we are actually we have actually just submitted, and it's currently under review, is combining this technology of soft reactive skins, soft robotic skins together with haptics. And so we have been investigating a soft haptic glove that a surgeon can wear during colonoscopy procedures. And these are some tests, user studies that we have done with our clinical collaborators, with and without wearing the haptic glove, measuring the NASA task load index with this surgeon, and trying and understanding how mapping the haptic forces during colonoscopy can help and potentially train novice surgeons, helping them, understanding how much they can push, and having them being able to map those forces directly on their hands. So I also want to talk briefly about other types of soft reactive skins, still with the concept of using soft optical sensing. And in this case, still for this project that we have going on in the lab, we have been investigating using soft optical sensors for potentially bleeding detection during colonoscopies. Like I said, when you are navigating with a colonoscope, you can potentially cause bruises and bleeding and so on, but you only have that visual feedback from the camera in front of you. So you don't know anything about what is going on in the back. And the back is actually pretty long. So you only find out that potentially there's bleeding or an hemorrhage once it's too late. And so what we have here is basically a soft optical sensor that is shaped in a U shape, and it's sort of like broken in the middle. And in the middle, we have a microfluidic channel. This is manufactured by using soft lithography out of SU8 pattern silicon wafers. And so when that microfluidic channel contacts blood within the colon, that blood can be basically sucked inside the microfluidic channel by capillary reaction, and then the sensor can potentially measure if there is bleeding within the colon. And this paper was actually recently published on Advanced Intelligent Systems. So the way that it works is, as you can see, the light is transmitted through and being picked up on the opposite side. And then as the blood enters the microfluidic channel, it can be detected. And we are able to detect different concentrations of blood within the colon, but also we are able to distinguish between blood and other types of biological fluids, such as bile or gastric fluid. And this is just an in vitro validation again, where we show in these colon model with synthetic blood that we were able to detect blood as the colonoscope is passing through with the soft robotic skin, with the soft sensing skin wrapped around it. So I think I have a little bit time left, and I want to just plug one last class of soft surgical robots that we're working on in the lab, which are hybrid soft foldable robots. And these are actually some of my, I would say, past works from my postdoc period. These are basically soft foldable robots in a sense that they sort of combine the best of both worlds when it comes to soft safety, soft fluidic actuation that is safe to use within the human body, but also they have rigid components strategically put in specific locations such that the robot can be folded down into tiny compact configurations. And so, for example, navigate its way to a specific target location for a surgical operation within the colon, and then they can unfold at the surgical site of interest by using origami-inspired techniques. And so, for example, in this case, I was using laser manufacturing, 2D layers, lamination, and soft lithography, as well as chemical surface modification to bond permanently soft materials together with a variety of rigid materials such as metals, plastics, and so on. And so that's how I achieved, for example, these hybrid soft foldable actuators that are so tiny and can be deployed and can be actuated by using fluidic actuation. In this case, it was water. They can, as you can see, they are really thin. You can embed microfluidic channels for pneumatic or fluidic actuation. And then in this case, these were actually made out of thermoplastic elastomers, or TPE, combined together with, again, rigid materials such as, for example, fiber reinforced plastics or stainless steel and so on. And in this case, these were deployable robotic mechanisms that you can mount on, again, traditional endoscopic instrumentation to augment its capabilities. So, for example, here, these would brace against the colon during colonoscopy, being deployed, brace against the colon, and provide a mechanical ground for the colonoscope to potentially sample tissue and provide the capability of more effectively perform output forces. So some of more recent work that we have going on in the lab, this is a paper that was actually published recently in Frontiers in Robotics and AI, is exploiting this idea of combining soft, foldable, so soft materials and rigid materials for neurosurgical applications. And so in this case, this is a robotic retractor. So something that can manipulate and displace brain tissue to create a cavity and access a brain tumor located in a deep location, deep-seated location within the brain. And it's funny because I was talking to my clinical collaborator about this when they reached out to me, really excited about the technology, and I was shocked about how they are currently doing this, because this is how they are currently doing this pretty much. It's sort of like a medieval type of surgical procedure, if you will. So they told me, like, yes, you would, open up the skull and then insert spatulas. You think about, like, long stainless steel rigid spatulas, almost something that I would use to cut my cake, right? So imagine doing that to your brain. What kind of effect that can have post-operatively, right? And so obviously this is, I would say, a really exciting type of application for soft surgical robots that can have a much more gentle type of contact with brain tissue. We were able to create this robotic retractor that is inspired by Murari origami, and then wrapped it around such that it would collapse down to a really tiny configuration, and then under vacuum, and then upon releasing the vacuum pressure, we have also embedded tiny micro actuators in between the Murari folds that can provide further extension. So we were able to see that this is actually performing quite well, not applying large forces within the brain. And we have tested this in vitro. Our collaborator, our neurosurgeon collaborating with us, suggested that we use tofu, as it apparently is really similar in terms of squishiness, I would say, with brain tissue. And so this is literally tofu pieces that we have put together to test and understand what type of force interactions we would be able to achieve. And it turns out actually that, because we are able to distribute the pressure, the forces around like a larger area, we are less invasive, obviously, than a traditional rigid instrument like this one. So I just want to, again, thank you for your attention. Thank you for inviting me, and a big shout out to my lab here and my sponsors and my fantastic collaborators. Thank you so much.
Or do you control actually the position there? Because I can see a lot of applications where there's a camera mounted and luminous interventions. And if you have a flexible or even soft manipulator, that will pretty much annoy.
Are you referring to this part of the talk?
No, it was earlier on where you showed a picture of the camera at the tip, and then there was a dot in the middle.
Oh yeah. Oh, so for this part of the.
Is that?
Yeah.
Is that just feedback of the position and position control, or is that a manipulator that is able to keep or to reduce the oscillation?
So this is based on the image guided control from the camera, yes. And the way that it is controlled right now is by using the 1 degree of freedom steering mechanism. Yeah, that it basically can not only help during navigation, but potentially steer the tip of the catheter of the robot once it's in front of the lesion. Potentially, yes, you could use also some of the concepts that I have shown later in the presentation. So these ones over here, for example, so structures like these that could also deploy and provide mechanical stabilization. So you would have, I would say, hardware mechanical stabilization and also software stabilization provided by the image guided control. Yes, that would be a really neat idea. So for this type of stabilization that we have used with the onboard camera, we have shown that we were able to achieve, let's see if I can go back to that one. We have seen that we were able to achieve up to, so this green bar here is actually the maximum error as the system is realigning itself, and it's about less than 200 microns. So potentially, if you were to add a stabilization mechanism, a hardware stabilization mechanism, something that would deploy and brace itself on the surrounding bronchi wall, you could probably even, achieve higher precision than that, and that would be obviously really neat.
Great. Please join me in thanking Sheila Russo again.